Hello everyone, myself Jyoti and today's topic is physics of semiconductors. It's a lecture third, part of lecture 3 only. So today we are going to talk about extrinsic semiconductor, basically about donor and acceptor impurities. So we know that when we take semiconductor material, we either add a p-type impurity like pentavalent impurity or trivalent impurity. So we have p-type semiconductor, n-type semiconductor. Now see, look at this diagram. So we have a semiconductor. In semiconductor, if you take germanium or silicon, they have 4 electrons in the outermost shell. So here, this germanium atom is there, this germanium atom is there. It is having 4 electrons in its outermost shell and it shares its electron with the neighboring atoms. So it forms covalent bonds with the neighboring germanium atoms. Now what happens when I add pentavalent impurity atom? Here I have added, or you can say doped, arsenic, As. As, it is having 5 electrons in its outermost shell. That is why it is called as pentavalent. Now when I add that pentavalent impurity in it, the 4 electrons from the outermost 5 electrons, it will be shared with the neighboring germanium atoms, and 1 electron will be the free electron, and that free electron, it carries the current. So that is what is happening. So when we add small amount of impurity in the form of substance with 5 valence electrons, then in case of germanium or silicon, the impurity atom may displace some of the germanium atoms in the crystal lattice, as I showed you in that diagram. 4 of the 5 electrons of the impurity atom will occupy the 4 covalent bonds, and the 5th electron will be free and it will be available as a charge carrier. Now, this energy which is required to detach the 5th electron from the atom is of the order of 0.01 electron volt for germanium, and it is of the order of 0.05 electron volt for silicon. Now this n-type impurity or pentavalent impurity which we add, it is also called as donor impurity. What is the reason behind that? Because here you are having one extra electron. 5 electrons are there. 4 electrons are shared with the neighboring germanium atoms, and 5th electron, it is free, which it is donating, which is available as a charge carrier. So that is why it is called as n-type impurity. It is called as donor impurity. Some of the common pentavalent impurities which are added in germanium or silicon are antimony, arsenic, and phosphorus. Now, what happens when we add trivalent impurity to a semiconductor? Look at this diagram. Here again, you have the same silicon or germanium structure where it is having 4 electrons in its outermost shell, and these 4 electrons, they are shared with the neighboring germanium or silicon atoms. Now, when I add trivalent impurity, trivalent in the sense, take the example of gallium. This is gallium here. All others are germanium, and in the middle I have doped it with trivalent impurity, which is gallium. It is just looking similar. It is Ge and this is Ga. Okay, so gallium, it has 3 electrons in its outermost shell. So this 3 electrons will be shared with the neighboring germanium atoms, and here I don't have a electron to share with the neighboring germanium atom. Here I don't have the fourth one, so there will be a vacancy, which is we call as a hole. So that is what happens. So when you add a trivalent impurity, then the impurity atom brings 3 electrons but occupies a site of a silicon atom, calling for 4 covalent bonds. Such an atom can readily capture an electron, thus establishing the fourth bond, and the impurity atom serves as an acceptor, because you are having the fourth whole place as a whole. It is not having anything else, so it will accept an electron so as to make those 4 covalent bonds. The captured electron is not available for conduction, but there remains a hole in the valence band. So these trivalent impurities make available positive carriers because they create holes. In case of a pentavalent impurity, you have one extra electron which is used as a charge carrier. Here what happens, you have they create holes, and which can accept p-type impurities. These impurities are consequently then called as acceptor because it can accept an electron, or p-type impurities, and the dope semiconductor, here it is called as a p-type semiconductor. So that's all about what is what happens when you add trivalent impurity and pentavalent impurity. Thank you so much.